Ames Research Center has played and will continue to play an important role in returning the space shuttle to flight. Ames has contributed to the safety of the shuttle in several ways. Computing simulations and lab tests generated new data for preparing the shuttle, and new facilities here will provide operational support during missions. During every launch, a certain amount of debris falls away. In order to understand this phenomenon, we needed to simulate the event without actually flying a shuttle. A technique called computational fluid dynamics, or CFD, is a method of using computers to simulate airflow over the shuttle wing during launch and re-entry. It requires millions of calculations, but it can deliver highly accurate results.
We've been working very closely with a number of engineers at Johnson for quite a number of years in developing our computational fluid dynamics tools. We've helped supply them with computational capability to analyze the ascent of the redesigned external tank, as well as to understand the debris environment that the vehicle has to go through as it's flying through the air. Even very small pieces of debris, when they're traveling extremely fast, can still impart a significant impact to the vehicle. And these are things that we have to look out for, that we're still at risk for, but that we have a very good understanding of what that risk is, and we can try to avoid it. The supercomputing facility here at Ames is absolutely unique, and it's the fastest operational supercomputer in the world, and it's really allowed us to analyze our data, compute our cases, and just do things that we never would have been able to do without this facility.
In addition to the Columbia supercomputer, Ames has several test facilities that are necessary to validate the CFD simulations with real-world data. One is the ballistic range.
The CFD folks thought they had constructed a pretty good code that would really predict the motion of the shuttle foam fragments, but they wanted to check it. So they said, look, you guys in the range, you fire maybe 20, 25 projectiles, see how they actually fly, and we'll see if we can predict them with the CFD code. What we're firing is a small disc-like projectile. It's about 1.4 inches in diameter. For these particular tests, we're firing at about Mach 3, or about 1 kilometer a second.
Another way of validating CFD results involved building a small model of the shuttle, 3% of its actual size, and equipping it with hundreds of miniature sensors. This allowed us to look at design modifications on the fuel tanks, fairings, and other areas of the shuttle that might improve safety.
We were looking at doing some fairly detailed measurements on a 3% scale model of the shuttle in its ascent configuration with the external tank and SRBs attached. Tests in the 70s were done as part of the design process. They really didn't understand the aerodynamics of the vehicle until they did the wind tunnel tests. And those tests were primarily concerned with the performance, some loads measurements, but certainly not the detail that we need to look at now to make sure that the vehicle is safe to fly and that the modifications that are being made will be safe. There's new measurement techniques, in particular pressure-sensitive paint gives a complete map of the pressure over the entire geometry. New types of measurements using optical techniques have made measurements possible that we couldn't do back in the 70s. So it really is a much richer database now that we're able to generate for the shuttle.
Those measurements helped validate our calculations and showed that the computational work matches the real vehicle fairly well.
The agency had to develop a few repair materials and techniques for treating damage to the shuttle's wings. One of the critical test facilities at Ames is called an arc jet. This is a closed wind tunnel that generates air speeds and heating similar to what the shuttle encounters during re-entry.
The agency was concerned that a debris strike would punch a hole in the wing leading edge, and so they came up with the concept of a plug. This is a typical plug configuration. It's designed with some curvature to fit over the curvature of the wing leading edge. Early in the test program, a lot of the plugs were failing, and we learned lessons from those failures. We knew we had to change the materials, we had to change the shape and the angles to really try to adjust this plug so that it withstands the entry conditions.
This data was passed on to another group of CFD engineers who focused on analyzing the effects of atmospheric heating on specific types of tile damage and the repairs that might be made to them.
One is the analysis of damage, and the other is the analysis of repair. The object of CFD is to analyze both and determine whether both are in fact good candidates for entry or not. you need on the order of 100 solutions in under 24 hours in order to put enough credible data on the table to make a decision. We had the ability to do CFD, but it took us 3 weeks to generate even one solution. During the Return to Flight program, we've moved the capabilities to the Columbia supercomputer. We can now turn around 100 solutions in under 24 hours.
After every landing, it's extremely important to closely examine all the shuttle surfaces for damage. In the past, this has been extremely tedious and a time-consuming chore done manually. One of our researchers developed a device that could speed up the task and create a much higher degree of accuracy.
We developed a handheld laser scanning device that helps the technicians. It speeds up their measurements tremendously, and it makes the measurements more accurate and more reliable. So you put the unit over the tile and you press a button and it takes a scan in about 2 seconds. They will know as soon as they take the measurement if there is a problem with that tile that needs to be repaired. So it takes a lot of the human tedious work out of it, and therefore I think it increases the safety because it decreases the possibility for human error.
Some of the ongoing support that Ames has given to the space program has been through our vertical motion simulator. The vertical motion simulator is actually a simulation of the space shuttle coming in through landing and rollout.
The simulator out here at NASA Ames Research Center is a fantastic simulator for us to not just practice normal landings, but to also practice emergency landings. Any type of failure that could possibly happen to the space shuttle on touchdown, things like blown tires or brakes not working, nose wheel steering, anti-skid, high crosswinds. It's a high fidelity sim and it's fantastic training. Another great thing about the sim is in the visuals, you can put runways from all over the world. So we train all of our backup landing sites. We have 2 runways in Spain and 1 in France. We can also land at Edwards Air Force Base in Southern California, White Sands in New Mexico. We don't really have the resources to take an airplane out there and look at all those airfields, so it's really efficient for us to come out here and see in the simulator.
There are very few off-the-shelf solutions. It really comes down to building spaceflight hardware. You need to use a lot of different disciplines and you need insights from a lot of different people.
I think we've been invaluable to the program as a center, and so it's been very gratifying to help the program move forward.
NASA Ames is committed to astronaut safety and mission success. All of these contributions add up to something we're very proud of, returning the space shuttle to flight as safely as possible, as soon as possible.